This problem is about merging case-sorted linked lists. We are not given how many lists there are, but we can kind of count them as we iterate over them. And we need to return a single merged linked list. Now, there are kind of three approaches that I want to show. The first one would be kind of the most obvious solution, but it would be not as optimal. Then I will go into a bit more advanced data structures to kind of break down the problem a bit further. And then finally, we will reach an optimized solution. So initially, if you think about the fact that we just have k-linked lists and we need to return a sorted list, we don't need to think about sorting until the very end. And so what we can do is actually just keep adding every single element of every single linked list into a single list and then call the sort method on that list. And that will kind of give us an initial solution. So we can do all elements list equals empty list, and then we can do for head in lists, and then while head dot all elements dot append the value, and then we simply can move the head. So head equals head dot next, and that will populate the all elements list. And then we need to consider the case where the list, well, there are no elements. So if not all elements, then we can just return none. Otherwise, we want to sort all elements, so we can just do in place sorting, and then we can have to build up the final linked list. So we can do initialize a dummy node that will be just so that we can start the list. And then we can do for node in all elements. We want to set the next node. So we'll do current node equals dummy. And then we want to set the next node equal to a new list node for that element. And it would be better if we say for element, and then we create that value, and then we simply move the current node again. So current node equals current node not dot next, so that the next iteration it will add the next value and until we finish. And then we always know that the start of the final list will be the next value of that dummy node. And if you run this, this should pass the tests, but we can do a bit better. So the next step we can take is that we kind of want to leverage the fact that all of the linked lists are sorted, and that's kind of the expectation around this problem, that we use the fact that we don't need to think about sorting the list, and so we should be constructing the final list in sorted format already. So instead of doing this, I just want to walk through this example. If you know that all k lists are sorted and that each element must be exhausted before a element with higher value will be added, then we can kind of reason that we want to keep track of whatever the minimum value is at every step that we are going in the, well, across the lists. So we still want to keep track of all of the lists that we have. So we can still have a list, and then we can add all of the heads for each list. So for head in k lists, so for head in lists, k list dot append head, and then we can determine what the length of the k lists is by using just length of k lists. So now that we have the heads of each list, the intuition is that we want to, if you're starting with some value, for every step that we think about in a loop, so we will be having a loop that will basically be iterating until we exhaust all elements. And one way of doing that is by basically removing the entire linked list once we have reached the final node. And so once we reach the final node, that will be set to none, and then we can do a removal on that to remove any empty lists. So we can do base case k lists equals k for k in k lists if k. And so this will eventually terminate the loop and once we have gone through all of the elements. The next thing is that we will be storing a list again, and this will be the final elements list. So final elements can be a list of int, and that will be set to empty. And we want to keep adding to this list as we go on, and this will be added in order. And within each iteration, so this is each step basically. And each step we want to find whatever the minimum is across all of the heads, and we will be only adding whatever minimum value there is. And so that way we will never actually add a value that is greater than whatever the minimum is. So for example, in the first list, we have 1 as the first element, 1 as second, 2 in the third. We will calculate the minimum as 1 across 1, 1, and 2. And then the next step, once we add those values, so once we add the minimum values, we will be removing them from the linked list. So we will be moving the head of that list from 1 to 4, and then from 1 to 3, and then 2 will still stay there because it's not equal to what the minimum is. But then the next step, when the minimum is calculated, it will be between 4, 3, and 2. And then in that case, 2 will be the new minimum. And that way, every single time we do this, we are guaranteed to always be adding the minimum value. And so we will be having a current minimum, and we want to set this initially to infinity such that we don't actually we can evaluate whether some value is the minimum. So we can do that by importing from math and equating it to infinity. And then in each step, we first want to find out what the current minimum is. So find current minimum across heads. So for I in range when k lists. And one thing, after we kind of remove empty lists, we need to recalculate what the length of k lists is. And then in our loop, we will be setting the current minimum to whatever. And this actually resets every single iteration because we don't want to we're obviously only considering the current minimum in that iteration across the k current heads, because we are only at any single step considering k number of head values. So we don't actually need to, well, we need to reset this every single step that we go. So in this range, we want to kind of check what the minimum is. So if k lists I dot val is less than current minimum, we set current minimum to k lists I val. And so once we know what the current minimum in our iteration is, we can actually try to eliminate those. Or in terms of elimination, what we're doing is we are adding that minimum value to our final elements list, because we know that that is definitely the next minimum. And at the same time, we are moving the head of that linked list to the next element. And so that way we are going to progress forward until we basically every iteration we will be hitting the base case, which will check if what we have moved to is none. So for example, if one list is shorter, after 6 it will go to none, and then that will trigger this case, which will remove it, and eventually we will exit out of this loop. So here, iterate across nodes to check for minimum. So we'll kind of doing the same thing. So when k lists, if k lists I dot val is equal to the current minimum, we want to add that minimum value to the final elements. So current minimum. And then at this point, we need to shift move head to next element. So k lists I dot k lists I dot head equals k lists I dot next. And that will be iterating for all k elements, and we would have moved the heads. So once we have finished that loop, then we will basically have a fully constructed final elements list, which is sorted, and then we can construct the final linked list. So we can have a dummy node again, and then current node dummy, and then for element in final elements, we do the same loop that we did in the first version. So for element, we are doing current node dot next equals list node element. And then lastly, we are moving the current node. And then we return the next, or the head of the list, which is dummy dot next. So if you run this, this should pass all of the tests, and this would be a closer solution to the optimal. The only problem with this is that we are recalculating the minimum within each iteration. So this is an on times k complexity where n is the outer loop, and then in every single inner step we are counting what the minimum is, which is across of the k heads that we have. And so we can do better by using a different data structure, which is known as a heap, which will allow us to reach on log n, because then we don't have to actually recalculate what the minimum is every iteration. And so this kind of draws on the same principles of leveraging what the current, the or sorting of the linked lists themselves. And for that, we will kind of be using a heap to um, always keep track of what the sorting is for all of the elements. So when we think about a heap, we will kind of be applying this on the k lists themselves. So when we are actually adding the elements to the k lists, we are keeping track of not just the head, but we also want to keep track of what the actual value of it is, so that we can directly construct our final list. And so instead of adding values to a regular list and then converting it into a final linked list, we will be simply adding directly to a linked list as we go on. And we will be kind of keeping the same overall structure, but we will not be having final elements, for example. We will not be having a we won't be needing to kind of construct the final list at the end. And we will not be needing to calculate what the minimum is across each head. Instead, we will be storing the value, and because we want to actually sort every single node in across all of the lists by the lowest value itself, that is something that a heap can naturally help us do, because heaps always sort by the lowest value first, using an internal tree-like structure, but using lists. So that will help us avoid having to calculate the minimum at each iteration, because we can actually store the value at that node. So when we add the value and the head, the only problem is, in theory, this is all that we need, but if there are two or more values that have the same exact value, then the problem is that a heap will kind of break down, because it does not know how to actually compare the equality on a list node. Because I mean, as heaps work, every single element is compared by the first value and then the second value and so forth. So it's important that there has to be some tiebreaker that is not going to ever be different. And so we can do either a counter or using an index like enumerator, and that will be a bit easier. So for I, we can just do for I in if you don't know the length up front, we can just have a counter set to 0, and then we can set that counter, and then we can have the counter incremented by 1, and this will avoid any issues when we are adding or removing from the heap. So the next thing is that we will not be using append anymore, as to use a heap that actually inserts in the correct order from lowest to highest, we need to use the heap push, and that will automatically sort all of the nodes in k-lists by the lowest value. And if lowest value, then by counter. So it is kind of on a first seen basis, it will be ordered. And we don't need to do, well, find your current minimum anymore when we're not doing the base case. Now this makes it quite simple because now we already know that the heap is sorted, and so the next minimum, or we need to extract all values. So the next min head, counter, and next min value counter head is equal to whatever is the first element in the heap, but we want to pop that heap so that we can make sure the next time we get the next smallest one. So we want to do heap pop and then we want to add the head to the next the current node. So we will be constructing the list, the final list already as we go. So current node equals dummy, and then current node dot next equals the head, and then we want to add the next head, well, the next node of that list if there exists one. So if head dot next, then we want to add that to k-list so that at this point we are removing one node from the k-list, but if there exists another element, we need to add that again for consideration, and this will be inserted again in the correct order. So k-list dot heap push head dot next dot val counter plus equals 1, or we should add that after. So counter and then head dot next, and then counter plus equals 1, and then this will keep going until the final value, and then we again return dummy dot next. And one more thing, every heap takes in the actual heap as the first argument, so we need to add that as a first argument and then wrap the whatever value we want to keep as a second argument. So that, and just a few things about how I'm calling the function. It is heap q, and the correct way to call it is heap q dot heap push. And when we are adding initially the heads, it might be the case that some inputs are empty linked lists, and so before adding it to the heap, we want to make sure that there is a head, and then we can add it. And again here, heap q dot heap pop, and we need to specify the heap when we call heap pop, and once we go to the next node, we didn't update the current node, so we need to move the current node to the next node. And so that should be it. And if you run this, it should pass. And this would be the most optimal solution, as we are not recounting or resorting the lists each iteration to find what the minimum value is. And so that's all for this problem, and thank you for watching.